Hi everyone. In this video, we will solve the exercise 2.11 of Higher Engineering Mathematics by B.S. Grewal. And we will try to write the detailed solution of each problem. Let us start from the first problem. The problem is prove that every Hermitian matrix can be written as A plus iota B, where A is a real symmetric matrix and B is a real skew symmetric matrix. So what do we want? We have a Hermitian matrix, say H. We want to write this matrix as A plus iota times B matrix, where A is a real symmetric matrix and B is a real skew symmetric matrix. Let us have the idea and then we will write the detailed solution of this problem. Let us check in the 2 cross 2 matrix. Suppose we have a 2 cross 2 matrix which is Hermitian. So this entry says A11, A12, A21 and A22. Now this matrix may be a complex matrix. So let us write entry ij as, let us write this entry by Hij. Let ijth entry of this matrix is Hij. So this one is H11, H12, H21, H22. Okay. Let us write Hij as Aij plus iota Bij. So this will be A11 plus iota B11, A12 plus iota B12, A21 plus iota B21 and A22 plus iota B22. Now what we are given? We are given that this matrix H is a Hermitian matrix. This H matrix is Hermitian matrix. It means H conjugate is equal to H. That is Hji is equal to Hij conjugate. So from here we have H11 is equal to H11 conjugate. That means A11 plus iota B11 is equal to A11 minus iota B11. So this A11 cancels out and we get B11 is equal to 0. So we have this entry 0. Similarly, this entry B22 is also 0. Let us check for the other two entries. Now, we also have that H21 is equal to H12 conjugate. That is A21 plus iota B21 is equal to A12 minus iota B12, and equating real and imaginary parts, what do we get? That A21 is equal to A12 and B21 is equal to minus B12. So let us replace this A21 by A12 and this B21 by minus B12. So we have that this matrix H is of this form. Now let us split this matrix into two matrices like this. A11, A12, A12, A22 plus 0 iota B12 minus, here it was iota was there, minus iota B12 and 0, and then let us take this iota to be out here. So now write this matrix as A and write this matrix as B. So what we have done, we have expressed this matrix H as A plus iota B, where A is this matrix. And what we wanted to prove, we wanted to prove that A is a real symmetric matrix. Now A is a real matrix now, because when we have written that Hij is equal to Aij plus iota Bij. So here Aij and Bij are real numbers. So A11, A12, A12 and A22 are real numbers. So this is a real matrix. And obviously this entry and this entry are equal. So this is symmetric matrix. Similarly, this is a real matrix as B12 is a real number, and as diagonal entries are 0 and these entries are opposite of each other, actually negative of each other, so this matrix is skew symmetric. So this way we have expressed the Hermitian matrix H as a sum of symmetric plus iota times skew symmetric matrix. So let us write the detailed solution of this problem. Okay. Okay. Solution. We wanted to write a Hermitian matrix as A plus iota B. Let H be a Hermitian matrix. And let us write ijth entry of H is Hij. Be a Hermitian matrix. As H is Hermitian, it means Hji is equal to Hij conjugate. And let us write Hij as Aij plus iota times Bij, where Aij and Bij are real numbers. Now this matrix H, which is whose ijth entry is Hij, we can write it like this: a matrix whose ijth entry is Aij plus iota times Bij. So this matrix can be splitted as matrix whose ijth entry is Aij plus iota times a matrix whose ijth entry is Bij. Okay? Let us write this matrix as matrix A and write this matrix as matrix B. So where what we have written? We have written the matrix whose ijth entry is Aij as A and matrix whose ijth entry is Bij as B. Okay? So we have expressed this matrix H as A plus iota B. Now what we need to prove, that this A is real symmetric and this B is real skew symmetric. Now as Aij is a real number, so this A is real matrix, and as Bij is a real number, so B is also a real matrix. So as Aij and Bij are real numbers, it implies A and B are real matrices. Now, what we are left to prove is A is real A is symmetric and B is skew symmetric. Now we have Hji is equal to Hij conjugate. So now Hji is equal to Hij conjugate, and substitute Aij plus iota Bij in place of Hij. We have Aij plus iota Bij is equal to it was Aji and Bji. plus a ij minus iota b ij. Now compare real and imaginary part. We get Aji is equal to Aij and Bji is equal to minus Bij. Now from this condition we say A is symmetric. And from this condition we say B is skew symmetric. So this is the detailed written proof of this statement. Let us move to the problem number 2. Here we have proof that every square matrix can uniquely be expressed as P plus iota Q, where P and Q are Hermitian. We want to express a square matrix as P plus iota Q, where both P and Q are Hermitian. Now we have done one thing in the class. Let us remember what we have done. That is, every square matrix can uniquely be expressed as sum of a Hermitian and skew Hermitian matrix. Okay. We will use this fact and prove this statement. Okay. So what do we want? We want to write a square matrix as P plus iota Q where both P and Q are Hermitian. Let A be a square matrix. Okay. By the above statement, we know there exist unique matrices, say P1 and Q1, where P1 is Hermitian and Q1 is skew Hermitian. And A is equal to P1 plus Q1. Now A is sum of a Hermitian and a skew Hermitian. But we want to write A as sum of P plus iota Q, where P is Hermitian and Q is also Hermitian. Now let us try to modify this sum. Write this as P1. We want to introduce iota here. So let us just multiply by iota and divide by iota. Okay, so this is the thing. So now we know 1 by iota is equal to minus iota. So this is P1 plus iota times minus iota Q1. Okay. Minus iota Q1. Minus iota Q1. Now write P1 as P and minus iota Q1 as Q. By writing so, we have written A as P plus iota Q. But what we need to prove here, P is Hermitian and Q is Hermitian. Now P is equal to P1 and P1 is Hermitian, so that thing is already done. Clearly P is Hermitian. Clearly P is Hermitian. Okay. So what we are left to prove that Q is skew Hermitian. That is, we need to prove Q conjugate is equal to minus Q. Let us calculate Q conjugate. Q conjugate is equal to minus iota Q1 conjugate. Okay. So this is minus iota conjugate and Q1 conjugate. Okay. So what is conjugate of minus iota? It is iota. And what is Q1 conjugate? Now Q1 is actually skew Hermitian. So Q1 conjugate is equal to minus Q. So this thing is equal to minus Q1. Minus Q1. So this is minus iota Q1 and minus iota Q1 is again Q. So Q conjugate is equal to Q. Sorry, we need to prove Q is Hermitian. So we need to prove that Q conjugate is equal to Q. So what we have proved that Q conjugate is equal to Q. It means Q is Hermitian. Okay? And this expression is unique as this expression of A as sum of a Hermitian and skew Hermitian matrix is unique, because otherwise there will be two expressions as sum of Hermitian and skew Hermitian matrix. Okay. Let us move to the problem number 3. Show that a Hermitian matrix remains a Hermitian when transformed by an orthogonal matrix. So here let us check what do we mean by transformed by a matrix. Transformed by a matrix. Okay. Now suppose we have two matrices A and B. Okay. If we want to transform this matrix A by B, what do we write? We do write BA B inverse. So by doing this, so we have transformed the matrix A by matrix B. So here we want to transform a Hermitian matrix by an orthogonal matrix. So let us, this Hermitian matrix is H and orthogonal matrix is A. So we want to transform H by A. So we will calculate A H A inverse, and we want to prove that this AHA is inverse is Hermitian. That is what we need to prove. AHA inverse conjugate is equal to AHA inverse. So this is the idea. Let us hit the problem. Okay, let H be a Hermitian matrix and A be an orthogonal matrix. Okay. H is Hermitian, that is H conjugate is equal to H, and A is orthogonal. It means A conjugate A is equal to I is equal to A into A conjugate. That is A inverse is equal to A transpose. Okay. Here we must note one thing, that there is a problem with this problem, that is there should be a real orthogonal matrix, otherwise this problem cannot be proved. Meaning that there should be a real orthogonal matrix, A, B, and real orthogonal matrix. Real matrix means A conjugate is equal to A. So this is the all the things we have, and what we need to prove. To prove that transform of H by A, that is AH A inverse is Hermitian. That is, we need to prove that AH A inverse is equal, conjugate is equal to AH A inverse. ये हमने prove करना. Okay, let us start. Now we know AB conjugate is equal to B conjugate A conjugate. Similarly, we can extend this result as ABC conjugate is equal to C conjugate, B conjugate, and A conjugate. We will use this result here. A H A inverse conjugate is equal to A inverse conjugate, H conjugate, and A conjugate. Okay. Now we have H conjugate is equal to H, so this is A inverse conjugate H A conjugate. Now we know what do we mean by A conjugate. This means transpose of the conjugate. So this is A inverse conjugate and its transpose, H A conjugate and its conjugate. Now as A is a real matrix, so A conjugate is equal to A, and as A is real, A inverse is also real, so A inverse conjugate is also equal to A. So this is A transpose H and A was A inverse. A inverse transpose is equal to A transpose. Now, as A is orthogonal matrix, it means A inverse is equal to A transpose. And A transpose is equal to A inverse. And now this is A transpose is equal to A. So what we have proved that A H A inverse conjugate is equal to A H A inverse. It means A H A inverse is Hermitian. So this is all with this problem. Let us check the problem number 4. This is easy one. Show that this matrix is unitary if alpha square plus beta square plus gamma square plus delta square is equal to 1. So one thing should be noted that we do not want to prove that alpha square plus beta square plus gamma square plus delta square is equal to 1. We are given that alpha square plus beta square plus gamma square plus delta square equal to 1, and we need to prove that this matrix is unitary. Okay? So what we are given that alpha square plus beta square plus gamma square plus delta square is equal to 1, and what we need to prove that this matrix is unitary. So if this matrix is A, we need to prove that A into A conjugate is equal to आइडेंटिटी मैट्रिक्स। ठीक, तो ये हमने प्रूव करना। तो लेट अस स्टार्ट। A into A conjugate. So what is A? A is alpha plus iota gamma minus beta plus iota delta, beta plus iota delta, alpha minus iota gamma, and A conjugate. A conjugate means conjugate as well as transpose. So A minus iota gamma minus B minus iota delta, beta minus iota delta, and alpha plus iota gamma. We need to prove that product of these two matrices is identity matrix. Let us start multiplying. Alpha plus iota delta into alpha minus iota delta. Alpha plus iota gamma into alpha minus, let us write in the next row. Let us write it here. Alpha plus iota gamma into alpha minus iota gamma plus minus beta plus iota delta into minus beta minus iota delta. Then next, alpha plus iota gamma into beta minus iota delta plus minus beta into iota delta into alpha plus iota gamma. Next, beta plus iota delta into alpha minus iota gamma plus alpha minus iota gamma into minus beta minus iota delta. Then we have beta plus iota delta, okay, into beta minus iota delta plus alpha minus iota gamma and alpha plus iota gamma. Now let us multiply all these complex numbers. Okay. Now this is alpha plus iota gamma into alpha minus iota gamma. So these are product of two complex numbers. One is, and another second one is the conjugate of first one. So if this is z, this is z conjugate, and this is always equal to mod z square. We can, you also multiply these two numbers using distributive property. So this is alpha square plus gamma square, and this is beta square plus delta square. Let us multiply these two numbers. Alpha into beta, then minus iota alpha delta plus iota gamma beta, and iota into iota square is minus 1, and this is plus 1 gamma delta. Then next, minus beta alpha minus iota beta gamma plus iota delta alpha minus delta gamma, and also beta into alpha minus iota beta gamma plus iota delta alpha plus delta gamma plus, sorry, next, minus alpha beta minus iota alpha delta plus iota gamma beta and minus gamma delta, and again this term is beta square plus delta square plus alpha square plus gamma square. Now this thing is 1. This thing is just 1 because we are given it to be 1. Okay? We are given it to be 1. Now this thing is just 0. Alpha and beta cancels out. Iota alpha delta cancels out. Iota gamma beta cancels out, and this term also cancels out. This thing is 0. Similarly this thing is 0 and this thing is given to be 1. So what we have proved that a conjugate is identity. It means A is unitary matrix. A is unitary matrix. Let us move to the problem number 5. This is the most simplest problem in this exercise. Show that this matrix is Hermitian. So we need to prove that A conjugate is equal to A. So let us calculate A conjugate. Let us first write A conjugate. A conjugate is 3, 7 plus 4 iota, minus 2 minus 5 iota, 7 minus 4 iota, minus 2, 3 minus iota, minus 2 plus 5 iota, 3 plus iota, and 4. And let us now transpose this matrix. After transposing, we get 3 plus 3, 7, 4 plus iota, minus 2 minus 5 iota, 7 minus 4 iota, minus 2, 3 minus iota, minus 2 plus 5 iota, 3 plus iota, and 4. Now this is A conjugate, and this is nothing but just again A. So it means A is Hermitian. A is Hermitian. Problem number 6. This is again similar problem as above. Show that A is Hermitian and iota A is skew Hermitian. So I'm skipping this problem and let us move to the problem number 7. Show that the following matrix is unitary. This is same as the problem number, I think, 4. Problem number 4. Yes, this was the problem. So we need to prove that this matrix is unitary. So we need to prove that A conjugate into A is equal to identity matrix. So let us start with this problem. Write A to be 1 by root 3, 1 minus iota, 1 plus iota, minus 1. And let us calculate A conjugate. A conjugate is 1 by root 3. Let us take transpose and conjugate in the single step. So this is 1 minus iota, 1 plus iota, and minus 1. So this is A conjugate. Let us calculate A into A conjugate. A is 1 by square root 3 and B is 1 by square root 3 1 1 plus iota 1 minus iota and minus 1. So this 1 by root 3 into 1 by root 3 is 1 by 3. Now 1 into 1 is 1 and 1 plus iota into 1 minus iota is 2. Then 1 into 1 plus iota plus 1 plus iota into minus 1 is 0. Then 1 minus iota into 1 minus 1 into 1 minus iota is again 0. And then 1 minus iota into 1 plus iota is 2 and minus 1 into minus 1 is 1. So this is equal to 1 by 3, 3, 0, 0, 3. So this is 1, 0, 0, 1. It implies A into A conjugate is identity matrix, which means A is unitary. Okay. So similar is the problem number 2. So I am skipping this problem here. And let us move to the last problem of this exercise. I think this is the second last. Express this matrix as P plus iota Q, where P is skew symmetric and Q is real skew symmetric. This is also one of the most simplest problem of this exercise. So what is this matrix? This matrix is 2 iota, 2 plus iota, 1 minus iota, minus 2 plus iota, minus iota, 3 iota, 1 minus 1 minus iota, 3 iota and 0. And let us split this matrix as two matrices. So in one matrix I am taking only real parts, and in second one I am taking only imaginary parts. This is 0, 2, 1, minus 2, 0, 0, then minus 1, 0 and 0. And this matrix is 2 iota, iota minus iota, iota minus iota, 3 iota, minus iota, 3 iota and 0. So this is 0, minus 2, minus 1, 2, 0, 0 and 1, 0, 0. And let us take iota out of this matrix. This is 2, 1, minus 1, 1, minus 1, 3, minus 1, 3 and 0. Clearly write this matrix as P and this matrix as Q. Clearly this matrix is skew symmetric. And Q is symmetric. So we are done with this problem. So we have the last problem of this exercise, that is, if S is given to be this matrix, prove that S inverse is equal to 1 by S times S conjugate, where alpha is e raised to power iota 2 pi by 3. Let us first explore this alpha. Alpha is given to be alpha is given to be e raised to power iota 2 pi by 3. And we know what is e raised to power iota theta. E raised to power iota theta is actually cos theta plus iota sin theta. So by using this formulation, what do we have? That this alpha is equal to cos 2 pi by 3 plus iota sine 2 pi by 3. Now what is cos 2 pi by 3 is minus 1 by 2 and sine 2 pi by 3 is root 3 by 2. So this is minus 1 plus iota root 3 by 2, and this term is very familiar, which is omega. So alpha is nothing but just omega. So note it down. Alpha is equal to omega. Write it here. Alpha is equal to omega. And let us erase this thing as we don't need this anymore. So we need some properties of omega here. So what are these properties? First one is 1 plus omega square is equal to 0. Second is omega cube is equal to 1, and omega conjugate is equal to omega square, and omega square conjugate is equal to omega. So these are the some properties of omega which we will need in this problem. Okay. So we need to calculate inverse of S, and we know if a matrix is invertible, then its inverse is given by like this. S inverse is equal to 1 by determinant of S into adjoint of S. So first we need to calculate determinant of S. Let us rewrite S. Now we will substitute omega instead of alpha. So this is 1, 1, 1, 1 omega square, omega, 1 omega and omega square. Now let is determinant of S. Determinant of S is 1 times omega square into omega square is omega power 4. And what is omega power 4? Omega power 4 is omega cube into omega 1. And omega cube is 1. So this is just omega. So this is 1 into omega minus omega square. Minus 1 omega square minus omega plus 1 times omega minus omega square. So this is omega minus omega square, omega minus omega square, omega minus omega square. This is just 3 times omega minus omega square. This is a determinant of S. Next, what we need to calculate adjoint. And we know what is adjoint of S. Adjoint of S is just, it is the transpose of the matrix of cofactors. So what first of all we need to calculate cofactors. Cofactors of row 1. So what is the cofactor of this entry? We hide this row, this column, and determinant of this thing. This is omega power 4 minus omega square, and omega power 4 is again omega. So this is omega minus omega square. And second one is negative with a negative sign. Cofactor of this entry. We hide this row and this column, and we calculate omega square minus omega. Next is cofactor of this entry. We hide this row and this column, we get omega minus omega square. Next is cofactors of root 2. So cofactor of this entry, we hide this row and this column. So this is omega square minus omega with a negative sign. Next we hide this row and this column. This is omega square minus omega. Next is we hide this column and this row, and this is omega minus 1 with a negative sign. Cofactors of row 3. Cofactor of this entry, omega minus omega square. There's this row and this column, omega minus 1 with a negative sign. Next is cofactor of this entry. This is omega square minus 1. Okay. So adjoint is what? Matrix of the cofactors. One is omega minus omega square, omega minus omega square, omega minus omega square. Then again omega minus omega square, omega square minus omega, and then 1 minus omega, omega minus omega square. So this we have done wrong. The cofactor of this entry is omega square minus 1. So this is 1 here. Next is 1 minus omega and omega square minus 1, and transpose. Okay. So after transposing, we get this matrix. Because this matrix is just symmetric matrix. So this is just same. So this is the adjoint of this. Now let us calculate S inverse. S inverse is 1 by determinant of S, which is 1 by 3, I think omega minus omega square. Yes, omega minus omega square. And then we have adjoint of S. So let us multiply this omega minus omega square inside the matrix. With each entry, we get 1 by 3 will remain here. So this thing is 1, 1, 1, 1 omega square minus 1 by omega minus omega square, 1 minus omega by omega minus omega square, 1, 1 minus omega by omega minus omega square, and omega square minus 1 by omega minus omega square. What we need to prove, that it should be 1 by 6 outside here. Okay, let us check what happens. Okay, now we need to just calculate these terms. These terms. Okay, let us calculate these terms. Is omega square minus 1 by omega minus omega square. Now write omega square minus 1 as omega minus 1 and omega plus 1. Omega minus omega square, take omega common, so this is 1 minus omega. Okay, so this thing is minus times omega plus 1 by omega. So this is minus 1 plus 1 by omega. Now multiply this by omega square and divide also by omega square, and omega cube is 1, so this is minus 1 plus omega square, and 1 plus omega square is equal to minus omega square, so this thing is omega square. So this thing is omega square. Similarly, this thing is also omega square. And let us now calculate this thing. 1 minus omega and omega minus omega square. So take, so this is actually 1 plus omega square is equal to minus omega. So this should be omega, only omega, not omega square. Easy. So take omega to be common. So this is 1 minus omega. So this term cancels out, and this is just 1 by omega. Multiplied by omega square and divide by omega square, we get omega square by omega cube, and omega cube is 1, so this is omega square. Easy. So but what we want in answer, we want S conjugate in the answer. Means answer should be 1 by 6 times S conjugate, that is 1 1 1 1 alpha square conjugate. Alpha conjugate 1 alpha conjugate and alpha square conjugate. Okay. Now we know omega is equal to omega square conjugate. So this is, write this thing as omega square conjugate. Omega square is omega conjugate, omega square is omega conjugate, and this is omega square conjugate. So this is 1 by 3 1 1 1 1 omega square omega 1 omega omega square whole conjugate. This is again s, so this is 1 by 3 s conjugate. We have must have missed 2 somewhere, and let us check the calculations once again. We might have missed 2 in the determinant. Omega square omega power 4 minus omega square minus 1 omega square minus omega omega minus omega square. Omega plus omega is 3 omega minus 3 omega square. This is 3 omega minus omega square. This thing is perfectly fine. We might have missed 2 somewhere else. No, I think we haven't missed. Okay, I'll see that where we have missed 2 or this answer is right, then I'll update. So this is all the exercise 2.11 of Higher Engineering Mathematics by B.S. Grewal. We will meet in the next video with next exercise. Thank you everyone.